Okay, so my talk today is kind of some case histories of some work I've been doing over the past several years with a company called Geophysical Insights. When Tom Smith, the man who started Kingdom, sold the company to some venture capitalists about 10 or 11 years ago, he wasn't happy to just retire for the rest of his life. His brain is too good. He just wanted to get out there and play some more. So he started working with a gentleman by the name of Turi Tanner, who's unfortunately now passed, on using multiple seismic attributes at one time. But instead of looking at the wavelet information, we look at statistical information in the multiple attributes a different way. And so Tom, when he started the company called Geophysical Insights, brought me on as the first geoscientist to work with the developers so that they didn't get astray and they kept the user interface something that was geologically and geophysically intuitive, which, you know, you can make a developer do anything, but it doesn't always necessarily work with the way our brains think. So what I want to do today, is go through some of the problems that we have as interpreters. And I've been interpreting seismic. Again, we're doing sample statistics. So every point on every trace, every sample on every trace, has an X, Y, and Z component to it. That's how it's lodged in the earth. That's how we know how to interpret it. So if we were using multiple attributes and we were taking all of those sample pieces, sample data, and throwing them up into a cloud, then they tend to fall out with natural clusters. So we're just looking for the natural clusters in a very crowded attribute space world that's dense with information. And the neurons kind of go through a competitive and collaborative way of seeking out the natural clusters. And then when they come down from the cloud, they're back in their XYZ position, but they're aligned in ways that show the true lithology of what's going on the earth. This was the one I was trying to explain. Imagine a cube. So on the left-hand side, you see a cube of seismic data. We go through the cluster analysis, the pattern recognition, and what comes out on the right side is what we were calling a 2D map. And each of these little platelets, each of these hexagon forms are each of the neurons, and they're independent of one another. The closer they are together, the more the rock properties are very similar between the two clusters. The further apart they are, the rock properties are more disparate. So what I was trying to show earlier is that if you take a conventional wavelet, say you've got 30 hertz data and your wavelet or your envelope is about 30 to 40 milliseconds, if you start looking at sample statistics instead of looking at peaks or troughs or zero crossings, and you have 2 millisecond data, you're getting 15 to 20 times as much information statistically out of your attributes as you would be just working with the wavelet. And so what we found is we can take data and upsample it one time or resample it to a higher sample count without inducing a lot of noise. So if I have 2 millisecond data, I will go to 1 millisecond. And why that's important is each of the multiple attributes we use all have their own wavelet. They all have their own waveform. So each trace and each sample has a little bit different information that it carries with it. So statistically, this is what gives us our clusters and how we look at the data in the earth when it comes back down in our 2D map. What we see, and here's a conventional wavelet tuning thickness, and this one is, I think, 12 milliseconds. And how we're able to use this data is the bin size of the seismic data, so 110 by 110 or 82.5 by 82 or whatever, by one sample. In this case, I use a millisecond. The only thing that confines us for tuning, because we are seeing stuff way below conventional seismic tuning, is the interval velocity of the rock at that sample. So if you're working in carbonates, your velocity's faster, you're not going to see as thick a rock. And if you're working in clastics, with a 1 millisecond sample, I can probably see down to 5 feet thickness, and that's regardless of depth. We're not interested in frequency, we're not interested in depth, this is purely sample statistics. So, what I'd like to go through real quick is I'd like to show some examples of where I've used this technology to what I believe is success in various plays and how I've solved interpretation problems. The first one is a thought flow, kind of a quickie overview of some work that John Adamic had me do for TGS in an area in central Oklahoma looking for the Merrimack, which is an unconventional resource play in the Scoop and Stack. The second one is some work I've done in Morton County because I've been chasing Yewa and Cook Mountain in Morton County for like ever, and have found the proverbial thick, wet AVOs, and who hasn't? Using classification in thin bed. This is a discovery I had for a client, an oil discovery in Brazoria County, and how classification can help in difficult structural and stratigraphic environments, especially if you're working the Permian or the Delaware and you're looking at carbonate on carbonate and you have all these unconformities, all this exposure and you know, just a nasty mess over there. Wolf Camp and the Bone Spring just tear me up. And then now I'm using it in the Delaware Basin, tying it as we're drilling wells and tying to mud logs to see where cherts and things like that lie. And then my last example is South Louisiana, Tuscaloosa, 19,000 feet, and it's gnarly data, and I'm still able to see the reservoir. So quickly, I'll go through those. This first one, as I said, was a challenge to me by TGS. They have all this wonderful data in the Scoop and Stack Play in Oklahoma, and their challenge was, can Paradise find the sweet spots in unconventional plays? We chose the Merrimack, that was the hot play going at the time, and to keep it kind of on the real side, we only used vertical holes because there's so much variability in the horizontals, whether you stay in the zone, whether you frack it right. I mean, there's so many variables. So we chose wells that were straight holes, been drilled a while. My youngest well was 2007, my oldest was 1980, all of which, or to some extent, produced from the Merrimack. Now, the objectives, of course, was to try to see if I could discriminate between the poor producing wells and the good wells. But the assumptions and challenges was that it's not, the changes in the production wasn't necessarily related to geology itself, and that the log curves being old curves, you couldn't always get really good permeability and density information out of them. And then isolating specific production in all wells through the perforated zone, because most of the wells that we're looking at perforated the whole Merrimack section regardless. They just did it, let's go blast it all, let's go on down the road, not think about it. So this is kind of the outline of the area. It's about 196 square miles. And what you'll see is I've taken the production that TGS provided me, and I'm looking through the cumulative production at each of the wells. The ones that have green on them are those wells which produce 25,000 barrels or less in their lifetime. And we're talking 1980 to 2015 or 16. That's really nasty production. The ones over here on the right-hand side, or the east side, that are in pink, are those wells where ended up being in the middle category, in the 40 to 90,000 barrel range. And then there was one outstanding well, the Efficacy well, at the far south part of the 3D. And that well, over its lifetime, had produced at that point, and it's still producing, 240,000 barrels of oil and 2.23 BCF. So I have my gnarly wells, my nasty wells, and I have one really good outstanding well. So I'm going to focus on what I think is going on in that well. And the data, this is a time map on the Merrimack itself. What you're doing is you're kind of on the shelf edge of the Anadarko, and you can see to your southwest, you're going deep into the Anadarko, and to the northeast, you're getting shallow out of on the shelf. I'm going to focus on the north-south or south-north arbitrary line here. And the data quality, of course, is TGS. It's beautiful. I have to say that because John's here too. But it was really good data. And it came to me as 2 milliseconds. I did upsample to 1 millisecond so that I could try to really be discrete in the information I was looking for. But this is a cross-section that goes from the Efficacy on the south side to the poorer wells on the north side of the 3D. And you can see the dip. But what's also important here is to look at how the section is expanding as you go down dip. So the Woodford in here is the primary reservoir rock. I mean, it's the one that donates to the Merrimack for all the production. And the Woodford is thicker on the south side than it is on the north side. That might help explain some of the production variances. But by and large, and I've pointed out the perforations in here, by and large, everyone just came through and just, yes ma'am.
Pardon me, I cannot see your arrow here, so I don't know where exactly I was.
Okay, so let me see if I can put a, I hate not having a mouse, okay.
We have a laser pointer to
Yeah,
your left.
to my left.
I don't know if it'll work on that screen, but
Let me just not put it in my eye, okay? Can you see that?
Yeah.
Excellent.
Okay, so there's thin little lines in here that where the perforations are, if you can see that. So most of all the wells perforated the whole Merrimack section. Now, interestingly enough, the Cassidy well had most of the Merrimack perforated, but it had two very distinct perforated zones at the bottom of the well. And I was challenged to do this and look at this different ways. One, I just created instantaneous volumes and used instantaneous attributes to see if I could see the sweet spot. TGS gave me inversion volumes, which I did use and found out later that they hadn't used any wells to calibrate the inversion in this area. So I did not end up showing any of the SOM results from that because it really didn't tie the wells well. And then I ran spectral decomposition, tried to figure out a specific frequency at which the Merrimack has its better zones. Then I isolated that frequency band, ran instantaneous attributes on it to see if I could further pull out the reservoir. Of all three the ways I tried to work this, just the first one, instantaneous, out of the batch, seemed to be the best fit. Now, what we do is we go through principal component analysis. This is a way of taking all 17 or 18 volumes that we create on the instantaneous side down to those that really have the most diverse amount of information that are the key for us to use. In this case, what Paradise does is we look at it line by line. And it gives us, the green line in the middle, gives us a median for the whole area. But I chose to look at a line that went through the efficacy well, and the results of which, eigenvector 1, you can see the top attributes that pop out. I looked at eigenvector 1, eigenvector 2, took note of those attributes that the machine was telling me, statistically, these are the best attributes for you to use in neural analysis. And I came up with a recipe, I call them recipes, I cook a lot, and of these attributes right here that I used in this analysis. Now, it doesn't look like regular seismic data because it's not. It's just, I call them chiclets. But they're basically one bin by one sample size, and they're colored by the number of neurons that you have. And when you bring them back into Kingdom, it takes that 2D color bar and stretches it out over a 1D space. So neuron number 1 down here, neuron number 100 up here. And they're all divided equally so that you can see any one neuron that you put your cursor on. But in this case, I noticed that down here at the bottom of the efficacy well, there were two neurons, number 71 and 72, that were in that well and not in any other wells. And incidentally, it happened to be coincident. The lower perforations right here happen to be the best resistivity and the best porosity in that well. So those neurons, those clusters, were picking out a rock property separate from everything else in the well. And so I focused on those two neurons, and when I can isolate them in the map, I can see everywhere in that volume. And I ran a volume that went from 10 milliseconds above the top of the Merrimack to 10 milliseconds below the base of the Woodford. So I covered in the south area, it was about a 300 millisecond window, and in the north area is about 250 milliseconds. So that's a big piece of volume to look at. And this is everywhere those two neurons occurred in that volume. Now I've sculpted it down to the zone of interest here. So this is where all these two neurons right here occur in that volume in this zone of interest. And what's important is, you notice all the pore wells never had either one of those neurons, or they just blasted it, little pieces of it here and there. Now the median group, the 40 to 90,000 barrel people, ended up being in this group of clusters right here, and the efficacy is down here with both of them. Now, what we can do in Paradise is we can take all those little chiclets and we can turn them into volumes because we know the sample thickness, we know the aerial thickness by bins, and all we have to do is apply an interval velocity, a net to gross ratio for the zone, we give it a porosity, and we give it a water saturation. And when I did that to this little dendritic looking thing right here that happened to be right at the efficacy, that's what I'm thinking is the key part of the reservoir, that lower perforation set, I come up with 118 million plus cubic feet of hydrocarbon bearing rock. Now I take that and divide that by 43,560, which is how many square feet there are in an acre, to get my acre feet. And I can take that times my recovery factor, and I've converted everything to BOE at this point to keep it even because there's oil and gas here. And when I did that, I got 613, 125 BOE. Okay? That's just off this one little, what we call them geobodies. Well, the actual for the well at that point in time was 611, 685. So I'm within 1% of being able to predict from my work with looking at sample statistics the production in that well. And since it's still producing, who knows, there might be 2,000 BOE left in the well. You're never going to get everything out of the reservoir. That's why you have a recovery factor. But I'm just saying that this is not only a way to be able to isolate your sweet spots and unconventionals, but then you can actually use this tool to help predict or estimate reserves when you do isolate the reservoir. Okay. Now, I've been working in Wharton County forever, and it's really tough to be able to discern what's a wet AVO or low saturation gas versus a good AVO. I mean, I don't think there's a person in this room who's been around more than 10 years who hasn't probably drilled a wet AVO. What I've learned is that you look for how these patterns are set up in a very specific sequence. Now, in this case, I've got this is a portion of Wharton County. The town of Wharton is actually right over here. And I drilled these 3 dry holes. I'll be the first to admit it. And doing a postmortem on a fat, thick, wet AVO is not fun to your investors. But there was this well right here, the basic. This well right here, which is tight, but they fracked the heck of it and got some gas. And then I've got a couple of wells down here that were on very small anomalies, and they're called the Nixon wells. So I have my secret sauce, which I'm not divulging, for Wharton County and Lavaca County in that area, for the attributes that I use, and it does involve gathers and it does involve AVO volumes. But I found that in the good wells, I had a very distinct set of neurons, one on top of each other. And I've colored these white and red because I am from OU and Boomer Sooner. You can color these neurons anything you want. Just don't pay attention to the color bar. But most specifically, this neuron and this neuron were key to really good production. And here's the basic, which actually, you see this little blue neuron coming in here, was gas on water, but did produce. And this tightish sand down here only had the white neuron. And I'm going, now let's go look at my dry holes. Okay, first one I drilled was this well right here, the Nixon well. And it was a beautiful 80-foot thick Yava sand, wetter than heck. Had a nice mudlog show, but it was fizz water. But the 2 key neurons are separated by other neurons. And then I went up dip and had another AVO up here. I'm going, well, I'm across the fault line up dip. Maybe that's where the gas went. No, it was wet too. And, I'm scratching my head. But if I'd had this, 10 years ago when I drilled these wells, it'd be a different story. I'd never drilled them. But again, I've got 1 key neuron. I don't have the red one. And I have this wet sequence in between. So when you really are tied in and calibrated to your wells, you can start to differentiate between low saturation gas using this technology and good wells. And this applies to onshore and offshore. So this next case is actually carbonate, and it's Austin chalk, and it's shallow Austin chalk. And I have 3 wells in here that produced a total of 158,000 barrels. 1 well produced 128,000 barrels by itself. So the other 2, which were drilled later, kind of sucked pond water on that. But it's key because the client had come to me after spending $12 million shooting a 3D, drilling pilot holes, trying to do horizontals, thinking it was a fracture-oriented play. It's Austin chalk, it has to be fractures. And then they say, well, we're tired of spending money, can you kind of help us solve the problem? And I'm going, well, I'll give it a shot. And one thing I noticed, I pulled a gather. Now these wells were drilled in the 60s, they've long since been plugged, but there's still a little bit of an AVO effect. Of course, you're looking at peak events, not trough events, because it's Austin chalk. And I'm going, maybe that's a key to porosity. And that's certainly not a hydrocarbon indicator in my mind, but it could be a key to better porosity. So I decided to run attributes on my FAR angle stacks and I created a FAR minus near times FAR volume because I'm kind of trying to accentuate the AVO, which I think is porosity. And what I get is I get a sequence of neurons, the yellow perfectly tying to the perforations in my key wells. But then I have all these red neurons underneath, and I kind of call those support neurons. And my thought is that anytime you have a reservoir, there's going to be some effect of that reservoir above it, either through vertical percolation, which is going to change the rock properties, or there could be dim outs or something like that that changes the properties of the rocks below that reservoir. So I'm always looking for packages, not just where I'm tying to the neuron where the perforations are. I kind of look at the whole package and see how it's different from everything around it. And in this case, when I isolate, again, the key neuron where the perforations are versus the support neurons, I get a pattern kind of like this. Well, it doesn't take your eye very long to think that maybe that's a channel, or that could be channeling, or that could be channeling over here. Certainly not along fault blocks. It's not associated with a fracture pattern in this area. So one thing that Paradise has to it is we're not only looking at the patterns in the neurons, but we have a volume called probability. Actually, it's called low probability, but everyone thinks it's anti-goggling to the way our brain thinks. And what it basically is telling us is that at any one cluster, all the data points in that cluster, the renegades who are on the very outside edge of that cluster are the most anomalous data points to that cluster. And I found in my experience that when I really look at those unusual data points, and I've used AVO volumes, that tends to be where the AVO anomalies are. So I thought, well, let's see what happens when I'm only looking at my anomalous data points. So I've turned everything off except those data points that are 10% or less likely to be in the center of the cluster. It's kind of how you measure it. So the ones in the center of the cluster are high probability of being close to the center, and they're like background noise. What you want to look for is the ones on the peripheral edge, the lower 10% or less. And what happened when I looked at it is all of the stuff around the production went away. Now let's look at this again. Okay, here we are. There's the production. There's the patterns around the producing wells, and I turn off all but the anomalous ones, and that pattern goes away. Well, that's telling me signs of depletion, because the production is not anomalous. It's not productive anymore. They've been plugged out. So here's a case where I have turned off the produced area, and all my other areas are still good, which means they probably still have hydrocarbons in them. And as it turns out, if you look at, okay, so the top of the Austin Chalk is an uncontrollable surface. It was subaerially exposed. It's going to get eroded. It's going to have channels in it. It's going to have a carbonate sand. And gosh, that's where the production's coming from, is a carbonate sand. And if you look, this is a flattened time slice at the top of the Austin Chalk, and in similarity, because we run geometric attributes too. You can see clear evidence of channels cutting into the top of the Austin Chalk. So here's a case where you can take a problem that you spent a lot of money on and one conceived notion, and you have to get it out of the box in your head and say there's other ways of creating porosity in a carbonate. Okay, thin beds. Now this is a discovery I had in Brazoria County, and a client came to me. He had an engineering buddy that brought him this idea on the back of a napkin. That's how it always works. So you have production in wells right down here, but it was poor production, so they had to be mechanical failures, because that's what engineers are always going to tell you, the mechanical failures. And you have this wonderful fault block, and then you have a well up in here that's produced 450,000 barrels of oil. So that sand has to be everywhere. It has to be all along that fault block. And my client said, what do I do? I said, well, buy a 3D, because no one's going to buy a deal from you without the 3D. And he said, well, I don't want to spend much money. So he bought me 8 square miles of 3D. Now this is an area just down from Chocolate Bayou, so I have tons of middle and lower Frio pays in here. And so he got me the 8 square miles that covered the essential part of the fault block. And you'll notice that there seems to be a little ridge going down the middle of the fault block. Well, the engineer said, well, that's a velocity pull down, and this goes high all the way into that fault. And I'm going, who taught you geophysics? So I'm going, well, let's just kind of look at that. And we did. And what I noticed is, one thing that's important when you're doing sample work is that no longer can you get away with sloppy synthetics. You have to be spot on in your synthetics and tied to the gnats, because if you interpret the wrong neuron, the wrong pattern, you can go down a rabbit hole that will not serve you well. In this case, the data quality was good enough that I got a really good synthetic. I had some good booming reflectors here that showed well. And the good well, the productive well, was tied to this wispy little amplitude. Most of us would have ignored that amplitude. And here it is right here. In fact, it was so light, you can barely see the peak event right there, that Kingdom wouldn't even map it. So what I ended up doing is I mapped the trough event above it, and then I used that trough event to flatten and go up and down and flatten time slices. And here it is along strike along the fault block. So here's the good well over here, and here are the poor wells over here. And that wispy little amplitude is just kind of going along there. And that black line represents a flattened time slice 17 milliseconds below the top of the trough. And I'm trying, this sand is called the Alabel, for those of you who are familiar with the area. And it can vary in thickness quite a bit. In this case, it was only 7 feet thick, and this is 10,800 feet. So when I did my neural analysis, I noticed that it looked like I had what I'm assuming, or what I'm interpreting, as an offshore bar, a very thin, small offshore bar. And if you'll notice, the reflectors below it are kind of flat, and it starts to have an arcuate shape, kind of like differential compaction. Hello, engineers. And if you had gone over to the fault, you would find no sand. So I showed this to my client. I kind of explained him and taught him geology. He was a financial guy, so he didn't know any geology. And kind of explained what I was seeing here. And if you go along strike, you can kind of see this guy coming along strike. And it gets pretty sparse over here where the poor wells are. Duh. When you flatten on it and you look at it, it looks like it has the shape of an offshore bar. The poor wells over here, which only produce 20 or 30,000 barrels of oil, are only on 10 or 15 acre pieces of sand. They weren't necessarily mechanical failures, they just were in very small reservoirs. And the other thing I noticed is I have this orange kind of cut right through here. I'm interpreting that as a possible tidal channel cut. You've got a really thin sand, it doesn't take much to cut through it. And what that does, it compartmentalizes the production at the good well. So if you look at the production unit, 80 acre laydown unit right here, and the well's been producing for a while, it looks like it's only going to get this amount of the bar. So I told my client to go 467, legal location, outside the production unit, and he drilled the well, having faith in that we would find 7 feet of sand at 10,800 feet. And we perforated 6 feet of sand. Here's our little channel, a little bar right here. And then we found 4 feet behind pipe in the grubs. Now, again, this is at 10,800 feet. Well below conventional seismic tuning, but these little neuron suckers are looking for patterns in the data, and they can see it because we're doing sample statistics and not wavelet statistics. Okay, this is some work that Patricia Santagrossi, one of our coworkers, has done in the Eagle Ford. And we had a client who gave us 290 square miles, gave us 170 wells, gave us all the production information, 10 full cores, a whole bunch of sidewall cores. So we had the wazoo to calibrate to. And she did an excellent job, and I'm not showing a lot of her slides, but this is one I like because this is 100 milliseconds. You got 3 wavelets here. And you go from the top of the Austin Chalk to the top of the Buddha. And in this area, the Eagle Ford is only 30 milliseconds thick. It is the trough between those 2 peak events because you've got 2 carbonates and a shale in between them. And what you can see, if you count them, and Jim Allen did this, he counted 14 different facies tracks in the Austin Chalk alone. So that's how much variability there is in the Austin Chalk when you get down to this level of detail. And the Austin Chalk is coming back as a play. Maybe this is a good place to go find some porosity. But the amazing thing about it is statistically, for 43 years, geophysics, or longer than that, but for my 43 years in the business, I've always wanted to get seismic information to the same scale as logs. And now what Patricia's done with a blow up of the Eagle Ford, and that's the Eagle Ford right there, she's been able to tie specific neurons to specific rock properties in the logs. So now we know where the sweet spots are. Now we can track it. And here's a well that absolutely missed the sweet spot. The sweet spot in here is this dark zone right here. They kind of missed it here. They hit a little bit of it here, and then they went out of it here. But she can tell by the amount of production and how well they stayed in zone whether they got the sweet spot or not. My favorite one of her work, though, is this one. How many of us would map along here, hit this little dump, and then keep on mapping? We just have a little low spot in our maps. Well, if you look at that low spot, is actually a karst coming down into the Eagle Ford from the Austin Chalk. So it'd be considered a really nasty, gnarly geohazard if you're trying to do horizontals in here. But you can not only see that it's a karst going down into the Eagle Ford, you can trace the last bit of deposition up dip, if you were to flatten on this, and see where the last deposition was that went to fill in that karst. You can't see that in conventional data. That's the beauty of sample statistics again, rather than wavelength. Now, this is some stuff I'm doing in the Delaware Basin, and I've got Chester, Lower Mississippian, sitting on top of Devonian. And when I got the project, my client had just reprocessed the data, and the consultant, who's an excellent geophysicist up in Denver, had given him, a map on the Chester and on the Devonian. And there, it looked like he was mapping on the full stack and mapping this peak event right here for both horizons. And his maps kind of looked wonky, so the guy said, okay, Deb, let's see what you can do. And so first thing I did is I had him give me a high resolution volume. This is the work of CIMAX, and they do very good high res work. It's post-stack, so it's not very expensive. But what it allows you to do is see a lot more detail in stratigraphy than just the regular wavelength data. But then I ran, okay, so in Paradise, you can throw in as many neurons as you want. If you throw in more than the natural patterns in there, you'll get some neurons that'll be breaking up clusters in little pieces. If you put in too few, it tends to assemble natural clusters into one big cluster. So you play with the number of neurons in there until you find the ideal situation. But you can use it to your advantage. So in this case, I kind of dumbed down the system. I used very few neurons, and I only used a couple of instantaneous attributes that are good for looking at stratigraphy, instantaneous phase being one of them. And what happens when you do that is you get your major depositional packages out and in front of you so that they're easier to map. So here's an example of the mapping that was done by the other consultant down here, the Chester and the Devonian. But you can start seeing the major bedding sequences, and you can start making maps that make more sense. So finally, after mapping the top of the Chester and the top of the Devonian, and this is my top of Devonian, and this was his top of Devonian, my Chester and his Chester, I got something that made sense. And then we could go about, looking for true structure, converting it to depth, and looking for true structure. So that's just kind of a way that you can get in carbonate on carbonate. And that happens in the Permian, it happens in the Delaware, it happens all over the world where you've got where you've got carbonate on top of carbonate. But what it also does, one of the major players in this area is this maroclastic dumps. And there's a lot of gas in these, but it helps bring out very simple features that you can then target. And what we're doing right now is we're going through and looking as we're drilling, and I'm creating synthetics as we're drilling, tying these patterns to what the mudloggers are giving me for information. Here's a case where I've got an 80-foot dolomite, and the top half of that dolomite is very fossiliferous. And that 40-foot zone right there corresponds exactly to that blue neuron. Now you leave that fossiliferous dolomite and you go into limey dolomite with some shales in it, and then all of a sudden your patterns changes. So these clusters are picking up very nuanced changes in rock properties that you can use to your advantage. There are a lot of people who don't want to drill chert. It may be good for kids to collect, but none of us want to drill it. And in this case, I'm able to use, the mudloggers information to help me define the neuron that represents the chert. Now, a lot of people say, well, you see a big garbage of neurons down here, and how do you know how to interpret that? Well, look at this mudlog, okay? This is Mother Nature here. You're going from limes, you're going from shales, you're going from chalk, you've got chert, you've got different colored shales, and then you have clastics. So this is Mother Nature in action. And this is why the rock properties look like they're all over the map when it comes to the chiclets. My last example, and I know you guys need to get out of here, I'm trying to talk fast, is Tuscaloosa in South Louisiana at 19,000 feet. I had a client who bought this well from a company here in town. This well was drilled in 1981, still producing, And this is the Austin Chalk right here. So this is the Tuscaloosa sequence of sands right here. And he tried and tried and tried to map it to figure out why this well's made 54 BCF and 1.4 million barrels of oil in its life. Because once you get off this key line right here, you cannot see that reservoir. So I created my attributes, and what I noticed when I was going through them is I noticed what appeared to be kind of a flat spot. So here's my lower Tuscaloosa sands, here's the upper Tuscaloosa sands, and the big marine sand, Tuscaloosa, sits right here. And the flat spot's right on top of that big fat marine sand. The perforations are 20 feet, done in 1981 right here. I think this whole thing is reservoir. But let's take a look at it. So here's my recipe. I don't have a problem showing my recipe, what I used. I did not have angle stacks. I did not have gatherers. This was purely done with instantaneous volumes. But hydrocarbon indicators like average energy and sweetness and relative acoustic impedance and things like that. And what I feel I brought out was I brought out the 1,300 acre reservoir for this well. And I could calibrate it to every other well. It's about 50 square miles of data. I could calibrate it to every other well in here who perforated or penetrated the Tuscaloosa perfectly. Now you're looking at a time slice cutting across a thinly laminated sand that's dipping. So you see evidences of braided stream channels within the reservoir. And when you turn everything off except the key neurons, then you can certainly see the reservoir, and then, like I said, I could go through and calibrate all the other wells. Now this is still one time slice. The client would not let me show the whole volume. Then you can see why that well produced from a different Tuscaloosa sand, not in this time slice, but produced 35 BCF of gas. So there's something to be said for pulling information out of gnarly data at deep levels using sample statistics. And with that, I'll summary and conclude that using geobodies and calculating hydrocarbons can be much more accurate using sample statistics. Drilling risk problems can be mitigated with the use of classification. Thin pays. I mean, if that was one example in Brazoria County, and Brazoria County is a big county, and there's 28 different pays in Frio, how many more of those wispy little amplitudes could be out there with 2 million barrels of oil in? I mean, there could be hundreds. That's 200 million barrels left to be found using this kind of technology. And then problems associated with correlating well logs in difficult stratigraphic environments. And this works on 2D and 3D. So if you're in an area that you don't have any 3Ds, that's not a problem. It's just raising the risk level a little bit by working with 2D in the first place. But understanding what each attribute is designed to give you as a result helps you with your interpretation when you get these clusters back. And with that, I'll take questions and say thank you very much for your time.
Questions for Deborah?
Okay, Linda.
So how long do you feel it took you to get the expertise to look that deeply into the data and all those different situations? Do you think that a novice could come in to do it, or what would you say the expertise level needed?
I can teach someone to push the buttons in 30 minutes. Interpretation is a skill that takes wisdom and understanding and using the right attributes. So people who are very deft with attributes and understand the meanings of them could be interpreting in a matter of a month or two and understanding what's going on in the rock properties. It certainly helps to have wells to calibrate to, but I've worked in areas of offshore Africa where I've had no wells. And you can still see the geologic forms. You can see turbidites. You can see reefs in West Texas. You can see these things because we're geologists and we're attuned to patterns in our brains, so that this makes it the perfect accompaniment for geologists to learn. Yeah?
Yeah, what sort of criteria do you use to determine like the optimum number of neurons?
Well, it's a not one and done thing. I play a lot. I will start out with a 3x3, 4x4, 5x5, 6x6, and I'll look at each one and there's ways to go into Paradise and look at the statistics that are associated with each neuron. So you can tell if you've clustered several neurons or several natural clusters together, and you can tell when you start splitting them up in little pieces that you can't interpret. But there's no way at this point that we can tell, because this is unsupervised. We don't know anything about that data until we get the information back for how many natural clusters are actually there.
Okay, and then a similar question, the number of components or vectors you would use in your principal component analysis?
You know, I try to keep, I use principal component analysis a lot as a first blush. Sometimes I make up my own recipe because I work some of these areas long enough, I know what works and what doesn't work. But I tend not to mix families of attributes. I'll do all my instantaneous at one time. So there's about 16 or 17 instantaneous attributes. I'll use all my AVO volumes, my intercept, my gradient, my flow factor in another family. I'll use inversion on rare occasions. I don't like inversion because I think this is a better solution than inversion modeling. But I keep the families, I mean, curvature volumes are very small numbers. They don't mix really well with wavelet information. So you have to kind of understand the families of attributes before you go into principal component analysis. Yeah.
Would you say the porosity is easier to track when you have the geobody identified, or is it just something that comes out depending on the neurons that you have identified?
Well, let's see, I'm Irish and lucky. It's one of those things, again, it's all about well calibration. That's where synthetics are important and you have to tie to a neuron that makes geologic sense. But if that neuron, as in Patricia's case, where she can go to specific zones in the Eagle Ford, ties to a zone that has 24% porosity, then that neuron, everywhere it shows up, is going to have those same rock properties. And I've got areas in West Texas where I'm looking at porosity inside reefs in the Pennsylvania reef play, where the porosities vary anywhere between 14 and 20%. And I can track each one of those neurons and can pretty much tell you which ones are the 10% porosity neurons and which ones are the 20% porosity neurons.
And you can do that by tying back to the well control, right?
Absolutely.
Okay.
Yeah, well control is that's what helps you reduce the risk in all of this. But you can reduce the risk if you have good well control.
And I do have a further question. Your volumetric example, stunning, really stunning.
Well,
1%, not just excellent. So
So
can you elaborate on that
well,
as being
if John will let me,
Okay.
he looked at that, he says, well, maybe that was luck. So he had me go into the 3 wells, and I didn't bring that because I'm not allowed to show that. The 3 wells, which were the medium case wells, and all of which had hit the key neuron. So I found the little dendritic pattern that appeared to be tied to those wells. And I got within 2% of their total production with the neuron patterns. So, and I've used it on a prospect I have in Wharton County. That's unfortunately leased right now. But I tied to a well down thrown in the upper Wilcox and were able to go in and produce within 4% the production from that old field, and tied that information back up to my prospect, which is about 15 BCF. If I could figure out who the heck had those leases, I'd go approach them. But
very impressive?
It's good.
And helped, no doubt, by high-quality data. So
not everything's good quality, especially onshore.
true.
So, any other questions? Yes?
Yeah,
Hal?
I just wanted to mention there's technical papers and other materials out there, some koozies, your beverage of choice, and there's also a particular paper that Deb's holding up right now about net reservoir discrimination that is in this month's edition of First Break. It's a combination of the process Deb has illustrated today and by various statistics. That was done by PMAX. Please have a look at that, those materials outside.
Yeah, PMEX is using this in all their business units right now. They're so on the samples bandstand, it's not funny. And this is an incredible way of pulling out how they've gone into a field and proven all the reservoirs using sample statistics. It's an excellent paper. Yeah.
Deborah, if we wanted a study done in our Austin Chalk field, we sent
Down for hire.
3D, what would be the approximate cost per square mile?
Oh, come on, David, give me a break.
I'll tweak his question for you.
That's an offline discussion, let's put it that way. But I will say this, as a consultant for the last 30 years, and getting into this technology about 8 or 9 years ago, 100% of my consulting work right now is using this technology to help people reduce risk, help them find porosity zones, help them prove up reservoirs. So it's if you can get on the bandwagon, I won't say it's a gravy train, but it's work, and I'm not turning it down. Thank you guys
We have
very
one
much.
more?
One more.
Yeah, I do, and, really enjoyed the case study examples. Thanks for sharing. It was a great presentation. You mentioned you gotta have time to play with it to dial in the right parameters. So instead of cost, I'll ask a time question. Is it fast to iterate through and choose a 3x3, 6x6? So is it a fast process such that the interpreter on the workstation can find time to play with it?
Absolutely. And, you know, I put a honker machine together just because I've been working, I just got through finishing a project that was 1,200 square kilometers offshore Bahamas, okay? And that takes a long time to chew through curvature volumes and multi-trace attributes. But a conventional workstation, you know, with 8 cores or 12 cores and 32 gigs of RAM can chew through 100 square miles of data in a couple of hours. So it's a very doable thing. I don't try it on a laptop. I mean, they're for showing things, they're not for doing things. But you know, a good workstation, and you can go through the data pretty quickly. Yes, ma'am.
Okay, what about the parameters? So do you change anything with the central random map parameters inside Paradise?
I'm playing with parameters all the time. I mean, like I said, this is not one and done. You play with it. You test different neurons. You test different combinations of attributes. The Austin chalk example wasn't really giving me what I thought was going on in there, and I just took thin bed out and put sweetness in, and all of a sudden it popped out. So you never know. And then once you've learned what works in an area, then you kind of keep that recipe in your cookbook, and you go on down the road.
So the training courses that are available are also highly worthwhile.
Yeah, we do training, and Hal's one to talk to there. But we have a beginning course that we have both an unconventional and conventional work that people can learn from and learn how to use Paradise. And then we have an advanced course that I put together that gets into the nitty-gritty about how you really do it. So I wasn't trying to make it commercial.
And that's why I stopped where I did. But Deborah, thank you, a fantastic presentation. We have our speakers for you. There you are.
How many of these do I have?
A few, I'm sure. Yeah.
Unless I start using them for slingshot bait, but who cares?
There you go.
At the Feral Hogs.
Deborah, thank you very much.
Thank you.
Wonderful presentation.
Thank you.
Meeting is adjourned. We hope to see you next week. Hooray. Thank you so much.